גם שוב. זה מפריע. Okay, so numerous papers we published showed that the environment doesn't have any effect of our long individual, and and I'm talking about disease prevalence, income variation, physical activity, lifestyle, and cognition. In each one of these classifications, we show that centenarians are resilient to environmental effect, meaning the environment doesn't affect them. So, what is affecting them? So here I present to you the clock, or the biological age. So if you look at the biological age, you see that our elite, the exceptional long-living individual, the centenarians, have their age is around 95 and older, but the biological age is like 20 years younger. We measured those biological age by methylation, which is a candidate for environmental assessment. So if you look at them, you see also that the control doesn't have or minimal effect, while the offspring, between the offspring of centenarians, has the same effect or the same prevalence as their parents. So we know that offspring of centenarians has some of the, let's say, the health performance of their parents, and we say, okay, if it's come from them, there might be some genetic insight. So how can environment affect on the offspring? How it can be translated to the next generation? So here we need to answer two questions. First, is the environment, where can we measure the effect on the environment of those people? And second, how it's inherited to the second generation. So, we can count, we can analyze how much genetics is in longevity. Like, sibling and whatever. And we know that the longevity or the genetic component in longevity is about 10 to 20%. And we know that the environment is negligible when we talk about centenarian. So what counts? What is the major effect of those guys to live longer? So what we think is the genetic and environment interaction, which label as epigenetics. And this counts for the 80-90% of the phenotype variance between the longevity variance that we see in people. So, and the next question, how is it heritable? For this, we came with the hypothesis, or I came with the hypothesis of the switch theory, which account for genome flexibility. So, just to illustrate for you what is switch theory, eyes on me, not body, on me, okay? Focus, let's start. When you come to a door, everyone can look at the behind, we have a switch, okay? And this switch is control the light. When instead of switch, which means the switch can do yes or no, meaning light or not. But if you replace this switch with dimmer, you can be more flexible in the amount of light that you have in the room, right?
Again.
If you have a dimmer, you know what is dimmer? Yeah, it's a button. Yeah, and you can, dim a little bit more, and then you can control, you have more flexibility in the way you want to see your light, right? Now imagine you have like 10 dimers like this, okay? So the flexibility is much more. Now let's turn back to biology. Imagine the switch or CPG site, meaning a place that can be changed by environment, the interaction that we talked about, okay? And so the switch are the sequence, and we can find them or look for them when we do whole genome sequence. But then we don't know if those switch do something to the light, so then we look for methylation percentage, okay? Methylation percentage is like the dimer that can say 10% light, 50% light, 100% light. And now the big catch, it's how it controls the light, and this is the expression of the gene, okay? With me, understand? Let's go. Now, this is just an illustration, but I will talk about it later as well. You see here that those are CPG island, the switch that turn on or off the gene. And you can see here, if it's black, it means it's turned on. If it's white, it's turned off, okay? So with aging, or with longevity, my hypothesis says that those guys have much more switches. And why it's important? Because if you have much more switches, you can adapt to any given environment. If you have only one switch, it's one environment. But if you have 10 dimers, you can do hundreds of environments. And that is why the environment doesn't control those extremely long individuals. Okay? So we can do many ways to come into turn on the gene and the number. We can play with the switches and the number of switches and how much methylation we have, and if it's turn on or turn off the gene. So in order to test my hypothesis, we gain an access to whole genome sequence of 150 centenarians and 150 controls. Remember, at the beginning, we need whole genome screen, whole genome sequence that we screen along this and trying to find CPG site which is the switches. Then we go for the methylation. It's okay to have switches, but if you don't turn it on or off, there's nothing that can be done, right? So in order to quantify the dimer or the switches or the methylation, which is the epigenetic effect, that's what we did. We looked of two types. One is HELP and one is Infinium, which screen the entire epigenome and look for methylation. When we're done with this, we went over to expression, meaning RNA-seq, to find out which one of the gene turn on or turn off. And everything is done in case control analysis, meaning the case are the E-line, what we call, is exceptional long-lived individual, and control, which are 30 years younger. So what you see in this slide is we screen the entire, as I said, 150 E-lines, 150 control. Those are Ashkenazi Jew from the New York cohort. It's not me. Okay, and those are from Italian, not Sardinian, Italian. Sardinian, I'm looking for you there.
It's the best.
Yeah, I know. And in those population, we see that there is excessive amount of CpG site. So we tag one of our hypotheses, meaning that ELIs has much more CpG site, much more switches, which means they are more flexible. It's a little bit messy, not messy, but overflowed. But I want to draw your attention to the red points. Each red point marks place where the methylation is higher in centenaries compared to control. And as you can see, there are hotspots around the genome, either with health tag or with the EPIC analysis. So we check mark the next one, which is we know that those CpG sites are used by those centenarians to maintain the environment stressor. And then we look for the RNA seq. And as you can see here, there is a difference between the ELI and control, and some of the genes are significantly different. Okay, so this is the third check mark, which means we started with the switches. We see that there is excessive amount of CpG site. We saw that there is hotspots of a methylation area, and this in turn affect the light, which means there is a significant expression of those methylated area. In this one, I want to talk to you about the protein, and I highlight two places that we talked earlier about the hallmark of genome. We talked about telomere signaling and adipogenetics. And why am I highlighting those two figures that we did we did a network analysis of those 14 genes that were significantly expressed, is because telomere, anyone know, it's part of the hallmark of aging, but the adipogenesis is because that when I said of our earlier analysis, we saw that most of the genes that were highlighted that associated with longevity are genes that have a link to adipogenesis. So it's confirmed what we found earlier in our population. The same happened here, again, adipogenesis pathway. To conclude, excessive amount of CpG site may provide regulation flexibility in genes involved in age-associated mechanism in a level that allow fine expression monitoring and thus adaptation to environmental stressor. This mechanism may promote longevity, and this is the thing. Such mechanism may exist in any resilience phenotype, meaning it's not necessarily associated with longevity, which is a good phenotype. It can do the same in, let's say, Alzheimer, that people has resilience to Alzheimer using this the same mechanism, or Parkinson, or whichever you think. And with this, I would like to have a year of healthy living, and all those pictures are of centenarian. This is the 100-meter dash runner. This is marathon. She's doing yoga, and she's smoked for 100 years. Okay. Any question?
Hi, thank you. This is really interesting. You hear about different levels of regulation, but it's really interesting to think that there's different amounts of regulation within certain levels of regulation. The first question is terminological. Why do you choose flexibility over robustness, let's say, when you're talking about regulation? right? Because you think there's like some optimal that you start at, and with age it declines. So that sounds more of like a robust system where you have more options for things to go wrong at specific sites versus flexibility where it's changing to a specific direction.
I don't think this way.
Okay.
I think robustness can be in the same gene, in the same spectrum. There is no need for excessive amount of genetic materials that can affect the whatever you look for. And flexibility, meaning it's to use whatever you want in the sense. And it doesn't mean it's when I'm saying flexibility, it doesn't mean that those let's say interaction between genes will fit a very stressful environment. It can be also a good environment. So there is no robustness in this case.
Okay. And the second question was, these CPG ends are these like differences, these extra CPG locations are heritable. They pass along.
That's why I'm saying it, because it's on the DNA. It's heritable. So if the centenarian has it, the kids has also.
But it's not always expressed in the kids. Or
No,
you don't
no,
really see
it's
it
not.
in the kids.
It's the meaning that you have a switch, it doesn't matter that you will use it, but you have it in case you need it.